Welcome to the second part of the online module on global navigation satellite systems. In the first module, we looked at some of the background on why it is hard to calculate our position if we don't have access to navigation systems. In particular, as a reading, I recommended you to watch a BBC video on the history of positioning. One of the most interesting parts of that video is that the presenter at the end makes a little experiment where he estimates his location on a lake by using sound signals, converting the sound signal into distances, and finally estimating his position through triangulation. It turns out that this is the basic principle of satellite navigation system. There are some predecessors. During World War II, a system of beacons was set up called LORAN, Long Range Navigation System, that was using radio frequencies to let users estimate their position exactly through triangulation, pretty much like our BBC fellow in the middle of the lake. This was, believe it or not, the main navigation system for decades. It was the high-tech system, and it was switched off only within your lifetime. It was switched off just about 10 years ago. There's plans to revise the concept and make it a terrestrial navigation system that does not require satellites, and this is due to new concern on space warfare and cybersecurity. This is a historical World War II era LORAN receiver in all of its analog beauty. This is one of the old LORAN towers built in the 60s. These were major pieces of infrastructure with massive amount of cost for building the stations, maintaining the stations, have personnel there to do maintenance and operations. This is one of the latest models of LORAN receiver. That's something that you might find on somebody's vintage yacht. And this is an example of the LORAN charts that were used to calculate your own position in the middle of the sea based on what signal you could receive from which LORAN stations. Now let's have a look at how this triangulation might work if we're using satellites instead of radio beacons. So in the course of this short module and the next two modules, we will answer to a number of questions. How does it work? Who runs it? How it is organized? What is the precision they can have? What can we use to improve the precision, and what's going to happen in the future in the next few years? By the end, my hope is that you will have a better picture of the myth and reality of satellite navigation. There's a lot of misconception about the way GPS works. People usually say that GPS is tracking you. We will actually see that this is not true, quite the opposite. And as an example, I like to use the Malaysia Flight 370. This is one of the biggest mystery in modern aviation history. That's a plane that literally vanished in the middle of nowhere a few years ago in 2014. It did have a lot of attention on the press. It periodically still has attention in the press because occasional debris is found, but we still don't know what happened to that flight. From what is relevant for this class is that there was some of the news coverage was focusing on why nobody could track this plane that vanished. And some of it was shockingly inaccurate when talking about GPS and how tracking is made. I have an infamous example that was a blog post on one of the technology blogs on the Washington Post. I really recommend all of you to read this when we are at the end, at the beginning of this module and at the end, and try at the end to spot the errors and see what the journalist got wrong. This is a conceptual figure of how GPS navigation works. We have a network of satellites, we have some big antennas and big control stations on the ground, and then we use GPS to track our movements, whether we are in a car, whether we're hiking, but planes use it, ships use it. In this particular set of slides, we will look at what is the mechanism behind it. And estimating the position with a set of satellite measurements, if we want to be specific, the acronym is GNSS, Global Navigation Satellite System. The mechanism behind it is basically a two-step mechanism. First, we estimate the distance between the receiving station, so what we've got in our pocket, or the big antenna on the plane, the car, the ship, and each one of the satellites. And then once we know the distance between receiving station and each satellite, we can estimate our position because we know the location of the satellites. And at that point, it's a triangulation exercise, exactly like our BBC guy doing that in the middle of the lake. So the primary measurement that is performed by a GNSS receiving station, whether it is a fancy GPS receiver on a military ship or the cheap one that you have on your cell phone, is a time measurement. What we measure is the time it takes for the signal emitted by the satellite to reach your receiver. This time traveled is then converted into a distance. To measure the time is easier said than done. The way it's actually done is exploiting the fact that each satellite is continuously generating and transmitting a unique sequence of binary data. We called it a pseudo-random code. So it's a unique sequence of zeros and ones that is transmitted all the time. And at every specific time, every specific instant, there's only one and one sequence only. Your receiver, fancy one, cheap one, can internally generate exactly the same sequence at exactly the same time. If at one point in time the satellite is emitting a 0, your receiver can, as a function of the time, say that at, I don't know, 1957.35 seconds and change, it's a 0. If it is a 1, it's a 1. We can duplicate exactly the same sequence. So at that point, the receiver compares the sequence internally generated with what is received. Because radio signals do take some time to come from space to Earth, by comparing the two sequences, we know exactly how late we get the signal from the satellite. So we have a receiver code and a satellite code. They will not be exactly in sync because it takes time to travel through space. The receiver will estimate this time difference and convert that into a measure of distance. Of course, you might know from previous classes and basic physics, or just by being a technology enthusiast, that electromagnetic radiation travels with some approximation at the speed of light. So once we have the time difference, we can convert it into the distance traveled by using this known speed. We can look at that in a plot. We have the satellite, and we have the signal that travels very fast to Earth. Because we know the speed, we can convert that in a distance, exactly like we would do it if I tell you that a car is traveling at a set speed, let's say 60 miles per hour, for a certain time, let's see 2 hours, multiply the two, we get the distance, is 120 miles. We do the same by measuring the time and then multiply that by 300,000 kilometers per second. So that's a pretty high speed. As often in this class, we need to deal with some jargon. For a technological reason and for heritage reasons, this distance is called the range of a satellite. Keep in mind that because the speed is very high, this time distance is very small. A common orbit for a GNSS satellite is 2,000 kilometers above Earth. That means that the travel time is just 1/10 of the second. So the development of GPS receiving station is actually an extremely high-tech development. You do have a remarkable piece of technology with you in your pocket. The second bit is the estimation of the position of the receiving station. So far, we just know how far we are from the satellites that are emitting this pseudocode, this sequence of random numbers. The position of the satellites is known. It's known because your receiving station, once again, have some respect for your cell phone because it is performing some remarkable calculations in real time. So your cell phone is calculating the expected position of each satellite at any given time. This can be done by implementing some equations on celestial mechanics. Once we have the position of the satellite and we have the distance from the satellite, then it's a basic triangulation exactly like we would do it on Earth. If we are on Earth and we know our range from a station of known position, one station only, well, we just know that we are somewhere on the circumference that has a radius equivalent to the range. If we can measure the range from a second known point, then we reduce the ambiguity to just 2 possible points, where we have a distance 1 from station 1, distance 2 from station 2. The moment we have 3, then we eliminate all the ambiguity and we have only 1 point. In space, of course, things are slightly more complicated, but not that much. So 3 measurements is the absolute minimum that we need to determine our position. If my receiver cannot receive the signal from at least 3 satellites, I don't know where I am. This happens a lot, and I'm sure it happened to many of you. If you switch on your cell phone and you look at your position in Google Maps and you are next to very tall buildings, or you are in a canyon, or you are under very dense forest cover, these are all cases where your receiver cannot get the signal of a sufficient number of satellites and it cannot calculate the position. 3 is the absolute minimum. In reality, and we'll get into that a little bit later, you need at least 4. And that's because there are some errors in the system that are quite unavoidable, and we can use some mathematical tricks to remove them. if we have spare observations. More measurements, more precision, but that's something that we will see in the next module where we will talk about it with some detail. So in space, the triangulation is very similar to triangulation on land, only that with just one measurement, we know that we are at some point on a sphere. With two measurements, we can be on a circle of all the points that are on the intersection between the two spheres. With three spheres, we still get 2 points, but it becomes fairly easy for the receiver to eliminate the impossible solution and give you the estimated point. So let's look at how we can do the triangulation. We are somewhere, let's say in the center of the US. We measure the time distance from satellite A, convert that into a range, time distance from satellite B, convert that into a range, time distance from satellite C, and we convert that into a range. We have assumed here that our internal clock is perfect. In reality, the internal clock in most receivers is not perfect. The onboard a GNSS satellite, there is a very expensive clock. Can cost tens or hundreds of thousands of dollars. I'm pretty confident you did not pay that amount of money for your cell phone. So the internal clock has an inferior quality. Because the satellite signal travels so fast at the speed of light, a very small imprecision in measuring the times results in a very big uncertainty in calculating the range. So I redrew exactly the same plot, but this time I'm accounting for some uncertainty, some error in the measurement of the range, because our clock is off by even just a small fraction of a second. This wrong distance, we call this the pseudo range. If we deal with pseudo ranges from 3 satellites, instead of being perfectly intersecting on the top of your point, like the 3 red circles that all cross exactly in one point where the receiver is, now we have some errors. So the three spheres don't intersect perfectly. We could be anywhere in the big 3D triangle between the three circles. To get rid of this uncertainty, we need to do a correction. And the way it's done, in fancy terms, that's called correcting the clock bias, is by correcting for this error in measurements. All of our receiver clocks, once again, are affected by errors. We can exploit, though, one little mathematical trick. If my clock is incorrect, well, that is going to affect the time distance from all satellites at the same time. If I'm a fraction of a second ahead, I'm going to be a fraction of a second ahead relative to each one of the satellites. Same goes if I'm a fraction of a second behind. So I can use a fourth measurement to correct for this shift in timing. It becomes a fairly simple mathematical problem. You do not need to worry about the math. We're not going to write down the equations, but you do need to know that the absolute minimum for estimating your position with any GNSS system is 4 observations. With this, we conclude this second module. In the next module, we will look at one specific GNSS system, the United States GPS. That is probably the name you've always used for satellite navigation.